So we'll start today with Ampere's circuital law. What Biot-Savart law tells, this is also going to tell the same thing. It is going to calculate magnetic field due to a current carrying wire. Question then arises, why do you need another law when you already have Biot-Savart's law? Biot-Savart's law is helpful for us when you are dealing with, small wires, because it uses the current element approach, and you integrate the current element and you find it. But if it is long wires, solenoids, there is one more thing called toroid. Toroid is now no more in your course. Toroid is like a ring, and on the ring there will be coil. It's a circular solenoid. So in those cases, Biot-Savart law becomes very cumbersome. So then comes Ampere's circuital law. Okay, now Ampere's circuital law is actually based on symmetry. This will be much like Gauss law and very, very easy. It will be based on symmetry, and it's a much more simpler thing. And the idea, okay, pardon my voice and tempo, the idea for Ampere's circuital law is very simple. Suppose you have a current carrying wire, right? I have a current carrying wire. The magnetic field, okay, due to a current carrying wire will always be a circular loop. So it's something like this. Say the current I is flowing in this direction, right? So I is flowing in this direction. Then where will I see? I will see a magnetic loop like this. Is this understood? The right hand thumb rule, right? So you can write, imagine a current carrying wire. So the idea, let's first see the idea. Imagine and read these notes, this will be sufficient for you. Current carrying wire. Imagine a current carrying wire, then you write, magnetic fields aligned along a current carrying wire are circular. Magnetic field lines along a current carrying wire are circular. Did you understand? This is a current carrying wire, and all the magnetic field lines around the current carrying wire will be circular. So Ampere's thought process was, why don't I go around one loop? I go around one loop and I try to find out what is the magnetic field. Means what it is trying to say, that suppose this is a wire and you want to find out what is the magnetic field at this point. So at this point also there will be a loop which passes through that point. Are you understanding? This is a current carrying wire. Let's say this is a current carrying wire. Or imagine here. Imagine that there is a straight current carrying wire. A little bit far away from the current carrying wire, distance r, you want to find out what is the magnetic field. So encompassing r also there will be a magnetic field line whose radius will be equal to r. Have you got it? So see, in Biot-Savart law, what they used to do, they used to break this current current carrying wire into small current elements. Here, what Ampere's circuital law will do, he will not go by the wire approach. He will rather go by the field line loop. And he will try to see what is the net magnetic field around the loop. Are you understanding? What is the net magnetic field around? So that will actually give you what is the magnetic field due to the current carrying wire. This is the idea. Is this much understood? There they used to break the wire. Here he will go by one loop. So the idea, it says that if you go around one closed loop, okay, go around one closed loop. Then let us try and see what should be the magnetic field. Okay. So let's now take up our process. Like, how will you calculate? And again, this will be applicable whenever you have symmetry. So write down your steps. Given a problem of Ampere's circuital law, also called as what you call ACL, step number 1. In Gauss law, what you used to take? Gaussian surface. It was a 3D surface. Here you will, in step 1, you will choose a closed path, which is called an Amperean loop. The first one is choose a closed path. Choose a closed path. There will be a current carrying wire. Our job is to choose a closed path around the wire. Every time it need not be circular, it may be rectangular also. It has to be a loop. Got it? So we will first take, let's for here we say that this is our loop and there is a wire and the wire is out here. The wire is actually passing through it. Have you understood? The wire is passing through this screen and you have chosen a closed path around the current carrying wire. This is known as the Amperian loop. Ampere's circuital law. Ampere, he was a French guy. His name is Henri Ampere. Okay, closed circular loop. Step 2. Move along the loop. Please understand, this loop is not the wire. The wire is actually going through the screen and you are now moving around the loop and you take tiny distances. Take tiny distances. And these tiny distances are like DL vector. DL vector means the loop has been broken out into tiny vectors which are not DL vectors at every point. At every point. So our concept is something like this. Let's say you have a DL vector. Let's say you have a DL vector. You have a DL vector and then you take a small DL. Like a DL vector, like this. A small portion and then there will be a DL vector. Okay. It won't be so big that it will be coming out. These are small vectors, DL, 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 like this. You take a small vector DL at every point. Okay. Now try to understand. You have magnetic, this is a magnetic field line. So what is the magnetic field's direction at a magnetic field line? The magnetic field will always be tangential to the magnetic field line. Okay, so let's say our magnetic field at any point here is, this is my magnetic field, right? This can be then broken down into two components. One component will be along this direction and one component will be along this direction. Is this understood? All right. So say this is the magnetic field, this is the B horizontal, and this is the B perpendicular. Similarly, in this loop, what will happen? If you go on this side, there will be again a B. So the B perpendiculars will be actually cancelling each other. And the B horizontal. So we write that you move along the loop and take distances DL, and every point the magnetic field B, the magnetic field is B, and you try to calculate something called B dot DL. Okay, at every point magnetic field is B. Achha, why it is B at every point? It will be symmetric. See, the reason is, this is a closed loop where the current carrying wire is exactly at the center. So every point is equidistant from the current carrying loop. So the magnetic field's magnitude will be same at all points. And deliberately we are trying to calculate B dot DL. Now somebody will ask, why are you calculating, why are you doing this dot product? Why not cross product? We are doing the dot product because in that case, we will be using the horizontal component. Dot product means what? B dl, there is a dl vector and there is a B vector. So you will be using the horizontal component of the magnetic field, which is the component along the loop. I am not bothered about the other one. The other one will cancel the other one. Yes, Samajh, did you understand this part? Okay, so write down, draw a closed curve along the wire, move along the loop, take a tiny distance dl at every point, and every point the magnetic field is B, and you try to plot the dot product B dot dl, and B dot dl will give you B dl cos of theta. We are interested only in this component of magnetic field along the path. We are interested only the magnetic field along the path. So this is of interest to us, the magnetic field which is of interest to us. Therefore, we are doing B dot dl equal to cos theta. Now you try to think, if theta is equal to 0, cos 0 is equal to 1, so B is cos 0 is 1, and therefore you will have maximum contribution. Okay, so cos 0 will be 1 and your contribution is maximum. Okay, pardon my handwriting today. And if theta is equal to 90 degree, cos 90 is equal to 0, contribution is also equal to 0. There is no contribution at all. So dl vector is along this line, BH is also along this line. Our next step will be step number 3. Add all contributions. Add all contributions. Each element is contributing B dl cos theta. So you actually add all contribution. So how to do that? You will be integrating along the loop for B dot dl. There you used to do E dot ds or E dot dA. Here you will do B dot dl. And when you do B dot dl, this is the contribution of, or the circulation of magnetic field. So let's get it again simple. Have a wire, imagine a closed loop along the wire. So I have taken a circle because it makes it easy to understand. Once you take it into a circle, this is a magnetic field line, or in our case, this is an Amperian loop. This loop has got a length. In this case, the length will be whatever is the radius, 2 pi r. This is not the wire. This is a hypothetical loop only. And this loop is considered for a small vector dl. And along dl, what is the magnetic field? That is, whatever is the magnetic field at this point, the magnetic field at this point is tangential to the circle. So take its horizontal component, that we do by BH cos theta. So we find ultimately not BH cos theta, BH itself is B cos theta. So B dot dl is evaluated, which is B dl cos theta. And if theta is equal to 0, theta equal to 0 means what? That my dl vector is along this side and my BH vector is also along this side. Then theta is equal to 0, contribution is maximum. And if by chance you take the perpendicular component, then it is at 90 degree. So that does not contribute to us, right? So we find one contribution, which is B dl cos theta. In such a way, we add all the contributions. If we add all the contributions, it is a closed loop integral along the loop, and we try to integrate all these B dl. Now this value experimentally has been found equal to mu naught times the current enclosed by the loop. There it was charge enclosed by epsilon 0. Here it is mu naught times the current. Let us say a current is flowing in this direction. Say the current, there is an I current which is going inside, right? So it is mu naught times the current that is enclosed inside. This is Ampere's circuital law. Ampere's circuital law tells us that if you are able to generate a symmetric Amperian loop, then B dot dl should be equal to mu naught times the current enclosed inside the loop. As simple. This is Ampere's circuital law. right? Add one more line. Meaning of this equation, just write this: B dot dl equal to mu naught IE, and then write the meaning. So Ampere's circuitous law tells us closed surface integral B dot dl is equal to mu naught times the current enclosed by the loop. Let us see what is the meaning of this. Write down what does the LHS mean. You can write down. The LHS tells you go around each closed loop. LHS is B dot dl. Go around each closed loop and add the tangential magnetic field. Go around each closed loop and add the tangential magnetic field. Go around each closed loop and add the tangential magnetic field, and the RHS tells you total current enclosed by the loop. Now we had learned that Gauss law is true but is not applicable every time. Similar concept is there with Ampere's circuitous law also. It is not that Ampere's circuitous law will fail anywhere. No, it's a law. So a law is always valid. Question is, there are two aspects. If you go by English, then you are trying to evaluate between truth of a law and utility of the law. Truth of the law is unquestioned. The law is true. A question arises, is the law useful every time? No. This law will be useful for us, you'll see, when B can be uniform. When B is uniform and constant, you can take out B from this integral. And then integrating dl is very easy. But if the B keeps varying, then this integration is very, very tough. So the law will not give you any help. So you can write down simplification factors are B has a symmetry. Like a long current carrying wire, the B is always tangential to the circular loop. So first thing you write, B has a symmetry. Simplification factors. B has symmetry, number one. Okay, just help me. I'll dictate more today. Second, B is same anywhere on the loop. B is same anywhere on the loop. B is same anywhere on the loop. And third is B is tangential to the loop. If it is tangential, then cos theta will become 0. Cos theta will become 0, and you will get the maximum contribution. If B is symmetric, then it is easy for you to simplify or conceptualize B. And if B is same, then B can be a constant and it can be taken out. You just integrate dl. Okay. So the 3 points have you written? B has symmetry, B is same at all points, and the third point you can write B is tangential to the loop. Then based on this, B comes outside the integral, or B goes outside integral, closed surface integral. Then your job becomes easy. B goes outside the integral, and closed surface integral dl then gives you L. Here, children, you have to understand. See, if you have taken a circular loop, then integral dl will be 2 pi r. If it is a rectangular loop, then it will be the perimeter. Integral dl is equal to L means L is the length of the loop. Loop is always symmetric. You can take a rectangular loop, you can take a circular loop, square loop, based on where we are taking what. But the dl's integration will be equal to the length of the loop. In our case, it is the circumference. And then your job becomes easy. BL becomes equals to mu naught I enclosed. And now we will see the application. Okay. So let's quickly revise what is Ampere's circuitous law. First of all, why do we need this law? Biot-Savart law helps us calculate what is the magnetic field due to a current carrying wire. But that law is applicable when we are having small wires which contribute to small current elements. The approach is easy. At that time we say dB is equal to IDL cross R divided by R cube. That approach becomes easy. But if you have solenoids or long wires, that approach does not help. Here comes Ampere's circuital law, where what we do, we take the current carrying wire and we try to imagine a hypothetical loop around it. Initially we will start with a circular loop. Once you take a loop around a current carrying wire, then the loop is a circular loop, means every point on the loop is equidistant, so the B at every point will be equal. And we take the horizontal component of B, which is actually along with the DL component, such that theta is equal to 0, right? That's why we try to evaluate B dot DL. B dot DL ensures that we are always considering the horizontal component and not B directly. B can be at an angle to that particular loop, but we will take B cos theta only, which is the horizontal component. Experimentally, the surface integral of B dot DL has been found equal to mu naught times the current enclosed inside the loop. This law is true, but this law will be applicable and beneficial for us only when you can assume a symmetric loop. B is symmetric, B is constant, and if these two things happen and B is also tangential, then you can pull out B from the integral. And in this circumstance, the integration calculation becomes easy, leaves you only to calculate the line integral, not surface integral, line integral DL, and DL will be equal to L depending on what shape you took, and the other side is equal to mu naught IE. So on the left hand side, what we do, we add up each contribution, so we integrate it. On the right hand side, it is mu naught IE. Okay, so much okay. So now we will take one example, and our example will encompass, like we'll try to do what is magnetic field due to an infinite straight wire. This one we will do. So this will be application. Now we are trying to find out magnetic field due to infinite straight wire. Biot-Savart law will not be helpful for us because this is not a small wire. Magnetic field due to an infinite straight wire. And this example will make your understanding more clear. Now here it is not a small wire, it is a big straight wire. So you can write down, suppose the infinite straight wire carries a current I, right? You have an infinite straight wire and this is infinite straight wire, okay? So this is going till infinity and it is carrying a current I. It is carrying a current I. So write down, suppose an infinite straight wire carries the current I and we want to find what is the magnetic field B, what is the magnetic field B at a distance. Distance is always perpendicular distance. What is the distance? This distance is R, and you want to find out at a point P what is the magnetic field. This is what you want to find out. Okay? What is the magnetic field at a point P? Have you understood? So the same thing, now I'm changing the orientation of the drawing, and I hope you will be able to understand that. Try and imagine that my point P is now, my point P is, why this thing doesn't, my point P is here. This is my point P and this is the wire through which the current is going. The same drawing, and say this distance is R. Is it clear? Same drawing I have reverted, okay? So step number 1, write down, choose the Amperian loop. Choose Amperian loop. And what will be your Amperian loop in this case? Circle. choose the Amperian loop is a circle. Every point is equidistant from the wire. Bracket you can write, every point is equidistant from the wire. So if you want to visualize it in this diagram, your Amperian loop is something like this now. Every point is equidistant from the wire. Okay. Number 2, point number 2 we write B is constant. Why B is constant? Since every point is equidistant from the wire, therefore the magnetic field at every point should also be constant. So your half the problem is taken care of. You can now pull out B. Third, B is constant, means the magnitude is constant. Third, field line is tangential everywhere on the Amperian loop. The magnetic field line is tangential everywhere on the Amperian loop or magnetic field. B, now I'm putting a vector, is tangential at every point on the Amperian loop. Let us understand what we mean by this. Let us understand what we mean by this. Suppose you want to find out what is the magnetic field here. This is the Amperian loop. On this loop, you want to find out. You want to find out what is the magnetic field. This is the magnetic field. Then you want to. This is the magnetic field. Then you want to find out where is the magnetic field here. Say on the next one, the magnetic field will be is tangential. Acha. Now understand one thing, okay? This is a current carrying wire. Forget Amperian loop. Then by right hand thumb rule, what can you imagine? You can imagine magnetic field lines, which you did in grade 10. This is a magnetic field line also. It is a coincidence that your Amperian loop is also sitting on one of the field lines. Understood? So on field, if this is a field line, then what is the magnetic field? Magnetic field at any point on the field line is given by the tangent. So here, if it is my loop, Amperian loop, then the magnetic field is tangential at every point on the Amperian loop. Right? Amperian loop gives you small elements which are known as DL elements. Let's try and understand. Amperian loop, let's say this is my Amperian loop. At this point, I can have a DL vector. If you understand this, everything will be clear. Amperian loop will have a DL vector and B is tangential at every point on the Amperian loop. Means at this point, if I try to look at B, the B is also in this direction. Our job is done. Right? That means you can write B is parallel to DL vector. Theta is equal to 0 and cos theta is equal to cos 0, which is equal to 1. Clear? So now apply Ampere's circuital law. B dot DL should be equal to mu naught I enclosed. What is the value of B dot DL? B dot DL, what is our value? We can take the B outside and do only for DL, which will give me what? B into 2 pi r. Here it will be 2 pi r. L is the length of the loop. The length of the loop will be 2 pi r. That means the magnetic field due to a infinitely long wire will be how much? This is, sorry. So if you bring up Ampere's circuital law, B into 2 pi r is equal to mu naught times, what is the current enclosed? The current is the I current that is flowing. Therefore, B is equal to mu naught I by 2 pi r. This is the current magnetic field due to infinitely long current carrying straight wire. In this question, we cannot take circle as a loop. Do you know why? Because you're trying to find it at a distance r. Sorry, a square does not work, because if you take a square, how can you justify that it is equidistant from all points? The diagonals will become more. Is this derivation understood? So consider a straight wire carrying a current I, then consider the Amperian loop, closed Amperian loop, which is circular with a radius r. Now the thing that we find is, since every point is equidistant from the wire, so the B is constant. The B is tangential to every point on the Amperian loop, which means B and DL are parallel to each other, and the angle between them is 0 degree, and BDL is equal to, sorry, B dot DL is equal to BDL cos 0, which is equal to B into DL. And if you can now take out, now since you can take out the B outside, it becomes integral DL, and integral DL will be equal to 2 pi r. So this is the expression. Okay. So some comparisons between Gauss law and Ampere's circuital law. Let's write down this also. Gauss law and Ampere's circuital law. Let's see what are the differences. Gauss law is actually done for evaluation of electric field. Ampere's circuital law is for evaluation of magnetic field, right? Gauss law works on something called the Gaussian surface, which is a closed surface. This is a surface 2D, and this is closed loop 1D. Then here we have charge enclosed, right? If you remember, this is closed surface integral E dot ds is equal to q naught by epsilon 0, and here it is B dot dl is equal to mu naught I enclosed. So it is charge enclosed, this is enclosed current. Ampere's circuital law, if a question comes, what is the usefulness of Ampere's circuital law? Ampere's circuital law can be used for straight wires, solenoids, toroids. Toroid is actually something like this. There will be a ring, and on this ring there will be a solenoid type thing. This is called a toroidal solenoid. This is a toroid, though not in your course now. So Ampere's circuital law is for straight wires, toroids, infinite current sheet. But Ampere's circuital law is not used for short wires, circular loops, irregular conductors. Not that it is not true, but here your integration will become difficult. Right? There is one problem also. We'll take up that problem too. But now our next topic of discussion is solenoid. I will just try, I'll see if we can finish solenoid, very good, else we will have a idea. Is this clear now? Ampere's circuital law, how to apply? There will be some problems where we can do. Our next discussion point is a solenoid. I don't know how much you remember from grade 10. So what is a solenoid? A solenoid is an arrangement of closely wound, insulated turns of copper wire, closely wound, of where if say the radius, if the radius is equal to say A, and if the length is equal to say L, then our L is actually much more than A. Solenoid is an arrangement where insulated wire, you might see that it is shining like copper, but it is actually powder coated and insulated, and they will be closely wound. Radius of a solenoid does not hold any importance later, right? And the length will be much long. And here we also get a term called N. N is equal to number of lengths, number of turns. per unit length or per unit meter. N is very important for us. How many turns per unit meter? This is a solenoid. Okay. Long insulated wire wound into many closed, what you call, shape. Now we need to, the beauty of a solenoid is solenoid will actually act like a bar magnet. A solenoid acts like a bar magnet. So if you see, you remember the clock face rule. Let's go to grade 10. Clock face rule. The clock face rule used to have, we used to say it as CWS. As you see from your side. Right? Now, if you see from your side, this current is going in what direction? The current is going in a clockwise direction. So here you will see basically a south pole on this side. And if you see it that the current is going in this direction, right, then you basically see a north pole. Let's get your basics first correct. Let's say grade 10, again grade 10, this is my solenoid. It's like a barbed wire on a building peripheral wall. Okay, in grade 10, how we used to learn it? In grade 10, we used to learn it like this. See, let the current go in this manner. Enough. Now if I stand here, I see the current in what direction? Clockwise direction. So from this side, if I'm viewing it from this side, okay, if I'm viewing it from this side, I see a south pole. And if I see it from this side, then I'll see the current in what direction? Anti-clockwise direction. So if you view it from this side, then you will basically see a north pole, right? And this is how it behaves, like a bar magnet. Means all the magnetic field lines will be coming in. I'm sorry, it's a very mutated figure. So they will all come like this. They'll originate from the north pole and come on the south pole. In grade 12, we will now try to find out what is the strength of the magnetic field of a solenoid. Very interesting concept. Okay, and we will be using Ampere's circuital law.